in linear algebra, the important subsets of R2, the two-dimensional plane, and of R3, three-dimensional space, are the lines and the plane, so the two-dimensional planes sitting inside R3. So one can ask, well, if we consider Rn for n bigger than 3, well, this is not a space that we can visualize in our head, but we can still describe it algebraically by just using vectors having n components. So we can ask for Rn, for n bigger than 3, what are the important subsets from the point of view of linear algebra? Well, these are actually called subspaces, and this notion of subspace will be introduced later. But it turns out that these subspaces are actually equal to the span of a set of vectors. So the notion of span of vectors is a generalization of the notion of lines and planes in 2- and 3-dimensional space. So this is one reason why it's important. So how can we understand what is the span of a set of vectors? Right? The previous video I mentioned the algebraic definition, and I tried to explain a bit what it looks like in 2- and 3-dimensional space. So they are those spans are just lines and planes, so things we know already. But how can we understand what the span of a set of vector is in a higher dimensional space? Well, one way will be to use the notion of basis. Actually, this is how we'll be able to talk about dimensions, but this will come later. For the moment, what I want to do is just to show you how to answer one basic question about the span. Right? So one way to understand what is the span is to try to understand which vectors are in the span, which are not. Well, by definition, they should be vectors that are linear combinations of the given vectors that from which the span originates. So how can we determine this? How can we determine if a vector is a linear combination of some other vectors, or if some vector belongs to the span? So let's look at one concrete example. Okay, so this is an important question for a few reasons. One reason will actually be mentioned, and the next theorem that I will present just after this example. So let's consider the following question. So let's see, this is some example. This is an example just in R3. So I can ask, is the vector 2, 4, -1 a linear combination of the two vectors 2, 0, -3 and 1, -1, -2. So here I'm using column vectors, because actually in this course we'll use mostly column vectors, so I have to get used to it, but if you understand how to do addition of row vectors for column vectors is the same, and scalar multiplication works the same way. So you can always take a row vector and turn it like this and get a column vector, and vice versa. So, right, so this will be the same thing as asking, is this vector in the span of, so maybe I could say this, is this vector in the span of, well, I can, all right, of these two vectors. Okay, so maybe I could write things like this. I'll put a curly bracket. Okay, so you can choose, you get two sentences, okay, but the middle part is just a bit different. But this is actually the same question, just phrased differently. So how can we answer this question? Well, if this is going to be a linear combination of those two vectors, Well, it means that I can find some scalars C1 and C2, although maybe in this case I will rather use x1 and x2 as variables. So I should be able to find x1. So I want to see if I can find x1 and x2 such that x1 times 2, 0, negative 3 plus x2 times 1, negative 1, negative 2 is equal to this vector 2, 4, negative 1. So if it is a linear combination, I can find really two numbers, two scalars, that let's say call them C1, so that C1 times this vector plus C2 times this vector gives this vector. Here I put x1 and x2 because I'm not sure if the answer is yes or no. Okay, so I view these more as variables, and I would like to determine if there's a way to give these variables some specific values, let's call them C1 and C2, for which this equality holds. Okay, well, it turns out that this vector equation is equivalent to a system of linear equations. So let me just rewrite this. So I'll just rewrite the left-hand side, right? Just using vector addition and scalar multiplication, the left-hand side, I can write it as 2x1 plus x2, right? Just the first component. The middle component is x1 times 0 plus x2 times negative 1, so I get negative x2. And the third component is negative 3x1 minus 2x2. So this is the left-hand side here. Right, so this vector equality is true if exactly when this is equal to 2, 4, negative 1. Okay, and so here I've got two vectors. Well, two vectors are equal exactly when their components are equal. So, right here I could have put that if and only if double arrow, right, which says, I'll put it in here. Right, it's not a vector. There are two arrows together. This, right, the arrow going from left to right says that if this is true, if this vector equality is true, then this equality is true. Okay, and the arrow that goes like this says that if this is true, then this is true. Okay, and now if this equality is true, then it means I've got a solution of the following system. So this vector equation is the same as the system 2x1 plus x2 equals 2, negative x2 equals 4, and negative 3x1 minus 2x2 equals negative 1. So I got a system here. Sometimes when you want to say that these three equations form a system, sometimes people will put also a curly bracket like this, okay, to say that all these equations go together. Right, so I've got a solution of that equation exactly when I've got a solution of this system. Okay, so, well, to solve a system of linear equations, in general, you form the augmented matrix, put it in row echelon form, reduce row echelon form, and then try to see if there are solutions or not. Here, well, might as well just stick with this system and see, well, x2 should be equal to negative 4, and then we'll just substitute in these first and last equations and see if I get a solution. So maybe this is the, in this case, this will be the fastest way to solve this system. Okay, so we could say, right from 2, we get that x2 should be equal to negative 4. Okay, and right, so I can plug this into 1 and 3. Plug x2 equal to negative 4 into 1 and 3. So what do we get? Right, so we get 2x1 minus 4 equals 2 for 1, and negative 3x1 plus 8 equals negative 1. Okay, so from this equation, well, if I isolate x1, I would get that x1 should be equal to, well, I put negative 4 on this side, I'll get a 6 divided by 2, so this gives that x1 should be equal to 3. Okay, and now we have to check, well, is 3 also a solution of this last equation? Well, yeah, if you solve this equation for x1, you'll get 3. Okay, so here this is a bit faster than writing the augmented matrix and doing all sort of row reduction. Okay, so, right, so this means that the answer is yes. Right, so the answer to your question is, the answer is yes. The vector 2, 4, negative 1 is a linear combination of those two vectors. It belongs to the span of those two vectors. Right? And we can make this explicit, right? So we can see, well, if x1 is equal to 3, if I replace x1 by 3 here, you get this. x2 is negative 4, so minus 4 times x2, which is 1, negative 2. Okay, this will be equal to 2, 4, negative 1. Right, so at this point, you should check that this is correct, right? So if you do something similar like this, you think you found a solution. You can plug the values of x1 and x2 and this equality, and then check that indeed this linear combination here is equal to this vector, to your given vector 2, 4, negative 1. Okay, so all right, so this means that all right, so the span of these two vectors will be a plane in R3, right? We take these two vectors are not parallel, okay? The span will not be a line, so it's going to be a plane sitting inside R3 in some way. And we're going through also through the origin. Okay, and this is a vector in R3, and it turns out that that vector actually is on that plane. So, so the vector is a linear combination of those two vectors, which means that it belongs to the span of those two vectors. Okay, so each time you see the word span, you should think about linear combination. So you have to recall the definition, or maybe if you recall some example, maybe that can actually help you also remember the definition. There is a direct connection between the notion of span, the notion of linear combination, and linear systems of equations. And it is given by the following theorem, which I will explain briefly, because the proof just consists of rewriting things a bit differently. So I will write the theorem on one half, and then I'll explain it on the right. So the theorem says the following. So suppose that we've got the augmented matrix of some linear system. So suppose that this matrix is the augmented matrix of a linear system. Is the augmented matrix of a linear system. So A will be the matrix of coefficients. B is the vector of constants on the right-hand side of all those equalities. Then the theorem says the following, that this system has at least one solution. Okay, so it has exactly one or infinitely many solutions. Exactly when, or I can say if and only if. Mathematicians like to say if and only if. I'm not sure if you have gotten used to it yet. But what I can also put, I mean, sometimes I'll write exactly when, or I put this double arrow. Right, so as a solution, if and only if B, this vector B, is a linear combination of the columns of A. Or in other words, if and only if B is in the span of the columns of A. So maybe I can even rewrite this here. So this is the same as saying that B belongs to the span of the columns of A. Of the columns of A. Right, so again, this double arrow means if what I've written here is true, so if the system has at least a solution, then you can go from left to right and conclude that B is a linear combination of the columns of A. But also, if B turns out to be a linear combination with the columns of A, then I can use the arrow going the other way. I go back there, outside of the screen, but it means I have to go back to what we had here. Okay, I'm just... I mean, ideally, maybe I should have put this one here, but then the things that they are too... I wanted to split the screen in this way, because I'll write the system here, and then I'll rewrite it in a different way underneath. Okay, so that's why the arrow, when I say go from right to left, I mean, what should be to the left is what's just above it. Okay. And same thing here, if the system has at least one solution, then you can go from left to right and conclude that B must be in the span of the columns of A. All right, so why is this true, actually? So this is not a difficult proof, it's just an exercise in rewriting things. So let me show you how this goes. Right, so A is the matrix of coefficients of some system of equations. So let me just write a few of those equations. So they will look like, so I'll write this here. Start with A11x1, right? So this will be the top left entry of A. Then we'll have the next one will be A12x2. Okay. If I assume that A has n columns, so the last entry here will be A1n xn, so it means that there are n variables in the system. All this equals B1. So this will be the first equation of the system. Okay, so I need to use a lot of letters because I don't know what A is precisely, okay, but the entries of the matrix A are denoted by lowercase a with two indices to denote rows and columns. Okay, so if we're on the first row, then the first index is a 1. For the second row, well, the first index should be a 2. So I'll just rewrite the same thing as I have on the first row, but I'll replace the first index by 2. And then this way, well, the second equation of the system is this equation. Okay, and if I assume that A is an m by n matrix, it means it has m rows. It means that the system has m equations. Okay, so I cannot write all of them, so I'll put these dots like this to denote that I skip many equations. The last one, well, I rewrite the same thing, but again, I replace the first index by m. So A m1 x1 plus A m2 x2, like this, plus, right, so I have to also skipped a lot of terms in each equation. I write the first two and the last one. So here A m n x n. Okay, this will be equal to B sub m. Right, so this is our system of equations, okay, that has this as its augmented matrix. And now what I can do is to rewrite this in vector form. which is, in the previous example that I've just done, we actually started with a vector equation, and then from it I obtain a little system with 3 equations and 2 variables. So here I'm kind of doing a bit the same thing. It's just that I can have a lot more equations and many more variables. Okay, I have m and n of these, and I don't know what these are precisely. Okay, so but the idea is the same. It's just really the notation is more complicated. So sometimes this happens in algebra. You see all these letters because there are so many quantities we don't know. But actually, if you understand a specific example with a few equations, a few variables, the general case is the same ideas. It's just the notation which is more complicated. Okay, so when this happens, just don't be scared because there are more letters. Okay, so there are not really new ideas. So here, what we can do, I'll use some different color. So I want to connect this with the columns of A. Well, the thing is that the columns of A, they appear here, right? So here I do have some columns. If I look at where I've got x1, I could sort of create some columns like this, right? So this is the column where the entries are all x1 times the entries in the first columns of A. Okay, so I've got the same thing for the second column, right? So if you write the system properly like this, then you can form a columns using all the second terms in each equation. Okay, if I go at the end of each equation, well, what do I get? I can put all these terms with xn together, okay, and I'll get also a column vector. Okay, and finally here, well, I get, if I form a column vector, I get the vector b, right, the vector of constants. So this actually can be rewritten. Right, I can write this. Here I've got an x1, so I can factor out the x1. Okay, and I will get, here I get x1 times the following vector. So this is a11, a21, all the way to am1. Okay, plus x2 times, right, so I factor out an x2 in all these terms. I'll be left with a12, a22, all the way to am2. Well, this is actually the second columns of A. Right, so the fact that the second index here is always a 2 means that we're looking at the second column of A. All right, and we do the same for up to the last term, right? So I do the first 2, then the last one, I can factor out an xn, and we're left with a1n, a2n, all the way to amn, like this, and all this equals, well, this vector, but this vector, well, this is exactly b, right? So I can just write b like this. Okay? Right, so this shows that, if this system is a solution, I can give x1, x2 up to x sub n some specific numerical values for which this equality is true. Okay? And then this showed that B is a linear combination of these column vectors. But this is exactly the first column of the matrix A. This is the second column of A. This is the last column of A. The nth column of A. Okay, so it's important to be able to see how to go from here to there. Okay, this will also be useful because after matrix multiplication is introduced, this will come soon, then we'll see that that system can actually be written as the matrix A times the column vector having entries, these variables, x1 up to x sub n. So I'll be able to write this as the matrix A times the vector x equals the vector b. And to understand this, well, it's important to also understand that this system can be written in this vector form. Okay, and well, this shows again that this notion of span and of linear combination, that if you just look at initially at the definition, doesn't seem to be too interesting. Well, it is directly connected with this problem of solving linear systems, and this is of course super important now in math and in all of science.